Okay. Hi again, guys. I hope you had a nice afternoon. We'll have the last session of today, and Marta and then Eleanor will present us the last before the last part on waveforms. Yeah, Marta, just take it away.
Thank you, Jean-Baptiste. So this first half of today's talks is going to be about mostly black hole perturbation theory and how we can apply this to build in spiral waveform models. And also I will just cover some aspects about ring-down modeling, but without really specializing a lot on that. Okay, so you have already seen some of this stuff in Anna's talk this morning. So in this lecture, we will focus mainly on linear perturbation theory. And linear perturbation theory, we will see how we can inform modeling for the evolution of memories, where, as Anna explained to you this morning, we have the perturbation parameter for our theory is provided by the mass ratio, which is mole. In the case of ring down, we want to study the ringing of the remnant that is produced by a compact binary merger. And you might think, okay, a merger sounds like a pretty violent event, but if we wait a bit, then we can still apply perturbation theory after the merger has relaxed to a perturbed Kerr-Schwarzschild black hole if we are just staying within classical GR. Okay, so I'm going to focus mostly on the Tucholsky equation because it's an equation that you can use both to produce some input that goes directly into things like Phi, so the fast Emery waveforms generator, but also to study more generically perturbations of Kerr spacetimes. So because it's so generic, I thought, okay, maybe we can just cover these rather than other equations that are specialized, for instance, on Schwarzschild spacetimes. Okay, so the Tucholsky equation, we are going to see how it looks like. It is a very powerful tool to study perturbations around the Kerr black hole. And the fantastic thing is that you can use it for Kerr, and Schwarzschild is just a subclass of Kerr spacetimes, so it's really valid generically in GR. The other very nice thing is that if you remember when we wrote the Einstein field equations, we said, oh, it's a lot of equations because it's actually 10 coupled PDEs. So it's kind of cumbersome to solve them, whereas Tucholsky equation is just one complex second-order differential equation. So it's much more convenient from a computational point of view that you have to solve that rather than complicated sets of coupled PDEs. And the other very nice thing is that it's separable into radial ODEs by decomposing the angular dependence into spin-weighted spheroidal harmonic modes, which we are going to see in a while. And as I mentioned, it has several applications. I'm just going to cover two that are computing the quasi-normal modes of perturbed black holes and obtain the necessary input for adiabatic link spirals. Okay, so first a bit of maths, but I will try to keep it light because this morning you had already some heavy session from Anna. So you need to introduce a set of 4 vectors that compose your tetrad. And this is one of the usual notations that you will see in the literature, and the 2 of these vectors are kind of special in the sense that they align with some special class of null geodesics that are related to ingoing and outgoing radiation. So in a sense, you can already see that this formalism is very suited to study radiation because 2 of the legs of the tetrads are already aligned with these null geodesics that are telling you about ingoing and outgoing radiation, which is what you want to study. And the other nice thing is that these tetrad legs satisfy certain relationships that greatly simplify the perturbation equations. So you get something much more simpler this way. And you can use this tetrad as usual once you fix a basis. Like in any linear space in algebra, you can then re-express all of the other quantities in terms of these basis vectors. And in particular, you can also express the components of your favorite tensors, like Ricci tensors, in terms of this new tetrad. Yes?
Wondering, so usually tetrads are like, so the E, A, mu, I'm used to seeing these two indices. So how does that relate to the L mu? Because this only
so for instance, say you want to write, wait, back. Okay, so for instance, if I write this guy in the curve, in Boyer-Lindquist coordinates for the curve metric, then I would say, okay, if I write it in those coordinates that are the usual coordinates, then I use this index mu, traditionally, and then I say, oh, the components for t, r, theta, and phi in Boyer-Lindquist are such and such. But I can also do the reverse and say, oh, I want to write a basis vector in Boyer-Lindquist coordinates in terms of these four guys, and then at that point you will work with these other indices. So it's just to say, if I use these, I work with another basis, and if I use the Roman ones, I work with the components expressed in my tetrad. So, and then
the E at the bottom that translates.
Yes, you always have this Jacobian. It's, you can convert from one to the other just by differentiating essentially the components one by one. Okay, so now we are going to introduce some other key quantities that are in fact what we then perturb and study with Weierstrass-Tucholsky equation. We can define these complex scalar quantities that are obtained by contracting the Weil tensor, which is defined here for n-dimensional spacetime. So this is the general definition. And you have 5 of these quantities that are complex because the tetrad is also made of complex vectors. So then you have all of these definitions. And you have that, so these are complex quantities, that they are 5, so 5 times 2 is 10 degrees of freedom, that are the 10 degrees of freedom, the Weil tensor. And how can we relate these to what we saw? We saw the Riemann tensor previously. And the Riemann tensor can be decomposed into a trace-free part, that is the Weil tensor, and a trace part, which is the Ricci tensor. Okay, so if you remember about well, you all know Einstein's field equations, and you know that the left-hand side contains the Ricci tensor, the Ricci scalar. So you can think that the Riemann tensor is related to the matter distribution, because matter goes on the right-hand side. So the trace-free part, on the other hand, represents the true gravitational degrees of freedom of the Riemann tensor. But what are the true radiative degrees of freedom once you gauge away all of the spurious ones? Those are the two polarizations, in a way, the 2 degrees of freedom of gravitational waves. And for instance, if you work in vacuum flat spacetime, remember that we had derived this when we introduced the geodesic deviation equation. In vacuum space-time, the Ricci is 0 because you don't have matter. So Riemann and Weil tensor coincide. And so you can then plug this into the previous definition of the psi, complex psi's, to show that in particular psi 4 asymptotically is related to the complex strain. So this again is a further confirmation that really this guy encodes information about these two polarizations. So don't be confused about the exact relation between these two, because you might see some factors sometimes in front of this that just depends on the tetrad normalization, so it's nothing big. Okay, so these two guys are 0 in the background, and so if I perturb them, I get that these perturbations are gauge invariant in linear perturbation theory. So again, they represent physical degrees of freedom, not just gauge effects. And in regions where they satisfy the homogeneous Tukowski equation, so no source, the two scalars are not independent. They are related by some identities that are called the Tukowski-Starobinsky identities. Okay, so now we mentioned earlier that one of the appealing properties of the Tukowski formalism was that we can, in classical GR, we can separate the perturbation equations into a radial part, which is this one on the bottom, and an angular part, just by introducing an ansatz for the solution, which is adjusted to the symmetry of our space-time. So here we factor out this azimuthal component because we know that we have axial symmetry in Kerr space-time. And then here we introduce some basis functions that I will mention in a while, and these functions satisfy this first equation, the angular part that you get by plugging this into the master equation, which is a bit more complicated. And here you have, on the bottom, you have the frequency decomposition. So for each frequency and LM mode, here in this decomposition, you get a different sourced equation, or not if you don't have a source. Okay, so let's talk a bit about these SLM functions that we saw. They are called spin-weighted spheroidal harmonics. They don't have to be confused with the spin-weighted spherical harmonics that we saw earlier and you're probably very familiar with. But as you see from just the decomposition of the master Tukowski equation, they come out as a natural basis to decompose our perturbation because they satisfy the angular part of the master equation. So then you might think, oh, yeah, but then eventually I want my HLNs. I always work with spin-weighted spherical harmonics. How can I relate the two? Okay, in Schwarzschild is very easy because the two functions are actually the same. But in Kerr, you can relate the two basis functions via some integrals that essentially give you the spherical spheroidal mixing coefficients. So they kind of overlap between the two basis functions for each a combination of indices. And as you can see from here, you can see that mode mixing between spherical and spheroidal harmonics in Kerr happens only between modes with the same M because, again, of axial symmetry of spacetime. Okay, so this is, yeah.
I saw in the equation, I think 2 slides back, there was an S, and I'm guessing that's related to the spin weight.
Yeah, sorry, this is the spin weight because psi 0 and psi 4 have different spin. So one is spin +2 and the other one is spin -2.
So I should fill in plus or minus 2
exactly,
in the S's.
Depending whether you can solve this for either psi 4, psi 1, depending on ingoing or outgoing radiation gauge. And then you have to replace these accordingly. And in here you can see, in fact, that the decomposition in L modes goes from 2 to infinity. Then when you recast everything in terms of spherical harmonics, you still start from L2 again.
So no monopole and no dipole.
Okay, so this is the first application of that we're going to see, adiabatic in spirals. So Anna explained this already, but let's just do a quick recap. We can apply the adiabatic formalism to intermediate and extreme mass ratio binaries, again, because we always have this small perturbation parameter that is provided by the mass ratio between primary and secondary mass. So we have these two classes. Sometimes people distinguish between intermediate and extreme mass ratio binaries. And orbits are expected to be inclined and eccentric with respect to the primary spin axis. So you are having a very, very complex mode structure that you can see here. All of these tracks correspond to different voices in a way that are associated to different combination of the fundamental frequencies that you have, because if you have generic orbits, you have radial, azimuthal, and polar frequencies, and you can have combinations of the three. And as Anna already explained, during the in-spiral, there is a natural separation of time scales. Orbital time scale is much faster than radiation reaction time scale. So what this allows is that you can essentially model your adiabatic in-spiral as a slow transition from one snapshot to the other, and each snapshot is essentially geodesic motion. And as Anna explained, this is all nice until you approach the last stable orbit, because then you start getting into the plunge regime where the motion is not adiabatic anymore, and so you cannot apply this formalism, and it just breaks down, in fact. Okay, so we're not going to, oh yes.
Can you maybe repeat what adiabatic means here? I don't really understand.
So it means that it's a kind of slow evolution that is driven by radiation reaction. So, and it means that orbital time scale is much faster, so you can average over the orbital time scale. You're not resolving all of the wiggles that you might have by trying to study also the orbital time scale details. So you average that out. And then the transition from, imagine in the simple case of a quasi-circular in-spiral, then you can say, I have first a circular orbit, then I just deviate a bit because I'm emitting gravitational waves, and I transition to another circular orbit with a smaller radius, and so on.
Mm-hmm.
But this is all happening because of this separation of time scale that you have. This is a bit the idea.
Okay.
And yeah, as Anna mentioned, I don't know if I have it here again, no, but it's also like some kind of conventional naming that in this phase expansion, the leading order term is called adiabatic, and then you have the post-adiabatic and so on. So we are just focusing on the leading order phase term that Anna mentioned this morning. Then in principle you can have I-order correction, but you need second order self-force to compute them fully. Okay, so these are our assumptions, and as I mentioned earlier, you have three different phases that describes the three types of motion, polar, radial, and azimuthal. And okay, so now you might wonder why did we introduce Tukowski equation? Because Tukowski equation, you can solve it to compute the forcing functions that you use to transition between snapshots and the amplitudes that are associated with each snapshot. Problem is that Tukowski equation is nice, but not so nice that you can solve a lot of Tukowski equations in milliseconds. So as Anna explained, what you do is that you solve all of these in advance. So you pre-compute all of the data that you need to compute the adiabatic in-spiral, so that waveform generation is fast. And the orbital parameters you evolve by flux balance laws, and I'm going to explain a bit better how this works. Okay, so obviously, for adiabatic in-spiral, you want a source term because your particle is there, and it's associated to a certain delta-like stress energy momentum tensor. So this is the equation very schematically that you need to solve. The source term is not as nice as the one that we saw, for instance, in this very simple example of circular motion on the first day, where it was just this integral of the stress energy tensor components. Because you're not solving the original Einstein field equations, you're solving another version that involves applying complicated differential operators and stuff. And so the expression is a bit convoluted. I haven't put it here, but you can go to see this paper, for instance. It gives you exactly the expression. Let's just say it still depends, of course, on the stress energy momentum of our particle, but you also need to project these components on the null tetrad that we saw earlier. Okay, so what you also leverage for Kerr geodesics is that in Kerr you can find, apart from the mass that is also conserved, 3 other constants of motion that are related to the presence of either Killing vectors or Killing tensor. So you have energy, you have the z component of the angular momentum, because again of axial symmetry. If you align your z-axis with the spin of the Kerr black hole, you have axial symmetry. And then you have this other constant, which is a contraction of this Killing tensor with the for velocity of the particle. And the conservation of these two guys is a bit more intuitive. This quantity is not so easy to understand its physical meaning, maybe. But for non-spinning black holes or in the weak field, if you take R to be very large, it can roughly be identified with the orbital component squared of the angular momentum. So it still has some kind of relation with something that makes physical sense, say. Okay, and in this type of formalism, also the adiabatic spiral, you often use also a certain parametrization that is called the quasi-Keplerian parametrization that also Anna mentioned. Here is just illustrated for you to understand a bit if we have a particle threading this torus of possible configurations, what the definitions are. So you have, this is the distance of closest approach, this is a pastron, and then you have these quantities that are called the semi-latus rectum, defined like this, and eccentricity. And you can see that, for instance, if these 2 points coincide, then that's a circular orbit, and eccentricity is 0. And then you have this other variable that define instead polar motion. So you can completely determine the evolution of the geodesics in terms of these three guys. Okay, so the radial part of the solution to Tucholsky equation has certain asymptotic behavior that contains some coefficients that represent the orbit averaged gravitational self-force contribution that is either regular at spatial infinity for this guy here, or regular at the horizon for this guy here. So these coefficients that you can extract from solving the equation are key quantities because they enter the computation of fluxes of the three constants that we saw earlier, so energy, angular momentum, and Cartan constant, to infinity and to the horizon. So once you get these two quantities from your solutions to Tucholsky equation, then you can also compute how these three constants of motions change along the spiral. And this is essentially what you need to update the position of the test particle under the influence of radiation reaction. So you have that the time average gravitational wave flux is a sum of two contributions, because imagine you are evolving, so you are emitting radiation not only towards infinity but also towards the horizon, because the horizon is absorbing radiation. So you have to compute these two contributions. And then you can plug these guys into some forcing term that you use to evolve your orbital elements that are the three variables that we saw earlier. So essentially, you see from here that by solving Tucholsky equation for each snapshot, you get some input that then is telling you how to update the position from snapshot to snapshot. And constants of motion are not constant anymore, but they slowly evolve under the dissipative effect of radiation. Then you need also some other thing, because for each snapshot, you need also to compute some mode amplitudes, because in the end, you want to have an expression like the one on the bottom. For each combination of M, K, and N indices, where these indices tell you how the three frequencies of motion combine together, you have to repeat these operations, say, and get, again, the amplitude from coefficients, from quantities that you get out from, once again, the Tucholsky equation. So then once you have done both things, you can put everything together. The phase you solve at the previous step, and then the amplitude you get again from this equation. So then you have the full signal that you want. And again, here there is a slight subtlety that here I'm writing an expansion in spin-weighted spherical harmonic, but I said I'm getting everything in terms of spheroidal. You can always recast quantities from one base to the other via mixing coefficients. So it's just a re-expansion. Yeah.
Yeah. So here looks like okay. So it's the adiabatic plunge in spiral. Okay. So the orbital elements, so the three constants of motion for the Kerr geodesic are being slowly changed by radiation reaction.
And then there are three equations for the phases.
Right. And so you get that change by radiation reaction through the Tucholsky equation.
Yes.
And here you're assuming it's only radiation reaction, but then, like, I don't know, if you have an accretion disk or some other environmental effect that also changes those things, can this be taken into account in this formula?
Yeah. You can include everything. This is just vacuum. So but then, for instance, you could have even resonances. And for resonances, then you need to modify how you do the spiral. So there are ways to incorporate these other effects because you can change the forcing terms to account for extra physics, but this is all vacuum.
Okay, what I mean to ask is basically, if you have these environmental effects, is this can you still use Tucholsky to get the radiation reaction, or is it not consistent?
I guess that it depends on the approach that you want to take. I mean, one way, for instance, would be to start from vacuum and just introduce some phenomenological effects in the forcing terms, I think, for the environmental stuff. Solving Tucholsky equation, it's going to be a bit complicated solving it with the environment because, when you solve it, you solve it for a test particle source in vacuum. And I'm not sure, to be honest, I'm not sure how easy it would be to extend it to the case where ab initio you do everything in an environment. Yeah. So, in my mind, it would seem much easier to try to do it post-hoc.
Okay.
So it's some kind of more phenomenological way.
I had a much more practical question. There was an index K at some point. How did that match up with L, M, and N for my harmonics?
Oh, yeah, sorry. This is just that I used the wrong,
so it's L or it's some combination?
No, sorry. You mean here? No, so this is different because, so this is a sum over all of these, guys. So LM is the index of the spin-weighted spherical harmonic.
Yes.
But here you have to sum over many contributions of this type.
Yeah. But what is the K? It's another index, or?
Yeah, it's another index for the polar motion. Okay. Yeah. But then you have a lot of combinations like this that you have to sum over, because you have a lot of harmonics that are related to the triperiodic motion.
Yeah,
so you have to sum.
The last equation is for Schwarzschild case, and that's why the K is 0 for the last equation.
In principle you have to sum over all of the indices here, because you always have this decomposition. You have a lot of voices. So if you want to be generic, this would be like a catch them all index that is NKN.
And then you also have to do the mixing between.
But this can be done before getting to this point. Yeah, but you have to sum over all of the voices that you're trying to resolve, all of the tracks. Okay, so this was just the application to the, yes, I'm doing well, to the adiabatic in spiral. And now I'm just going to be super brief about how we can use also linear black hole vibration theory for a ring tone. Okay, so you might have seen normal modes, vibration modes of strings in your classes, and you have to solve a wave equation with some boundary condition, and then you know that you can write the solution as a superposition of normal modes. And these normal modes are characteristic vibration frequencies that are related to the tension and density of the string. So you can kind of make the same parallel and say, okay, if I perturb a space-time, I'm going to have a similar situation in which I excite a superposition of frequencies that are telling me something about the properties of the black hole that was created after a merger, for instance. Okay, so in black hole spacetimes, you don't have conservation of energy, so energy is dissipated because we said horizon is also absorbing radiation, and energy is going out to infinity. And there is also a potential term that appears in the wave-like equation that you have to solve to get these ringing frequencies. And the precise form of this potential equation, or this potential term, depends on some gauge choices that you make. For instance, in Schwarzschild, you have the Reggie-Wheeler gauge master equation, the Israeli master equation. Or for Kerr, you have a reformulation of Tucholsky that is called the Sasaki-Nakamura equation. They are just returning the same spectrum, because for Kerr spacetimes, you have a nice property that is called isospectrality. You can transform one potential into the other and always get the same quasi-normal modes out of these equations. So this is nice because it means, for instance, in Kerr spacetime, you can perform a transformation that makes your potential term nicer from a computational point of view because of these decay properties. And this is what is achieved, for instance, by the Sasaki-Nakamura transformation. But again, we can make this connection with the vibrating modes of a string and think that these quasi-normal modes are vibration modes of our perturbed spacetime. And because of what we said earlier, they are not real valued anymore. They are complex valued quantities. So that's why also they are called quasi-normal modes. And these modes satisfy physically meaningful boundary conditions in the sense that what you want to achieve from a perturbation is that nothing should come out of the horizon, because it would be a bit strange. And then nothing should come in from infinity. So when you solve your perturbation equations, you want to impose these two conditions. Okay, so we said that in the case of these modes, for each LM index, we have a discrete set of complex frequencies that are labeled by an extra index that is marking the number of overtones. So you have a tower of quasi-normal modes for each LM index. The real part is giving you the oscillation frequency, because you have to take e to the I of this frequency. So this is the oscillatory part. And this is giving you the damping time. Well, actually the inverse damping time. And fundamental mode N0 is the least damped mode, so the one that persists the longest. So you have many methods to compute these frequencies. I'm not going to do into this, but I just wanted to mention that this is something that is used routinely in waveform modeling, because what we do, for instance, in phenomenological models is that we compute a lot of these QNM frequencies in advance, and then we create some fits, and we use the fitted frequency of the QNMs in our ring down model. And I'm going to explain this a bit later. This is an example of an ansatz for our merger ring down signal. This is in time domain. So here we are inspired again by linear perturbation theory. We have some amplitude, some phase, and then we have this term, which is essentially encapsulating what I just mentioned. You have this frequency that is given by the real part of the quasi-normal mode, and this is the inverse damping time that, again, you can compute from principles. And you might also see that you have some other terms. These are amplitude and phase terms that have complicated expressions with coefficients that are fitted to numerical relativity simulations and test particle waveforms. So though this ansatz is inspired by linear perturbation theory, because this is the kind of superposition that you get in linear perturbation theory, you have these other terms that effectively try to capture other nonlinear contributions in the ring down signal. An example of how we can apply what we saw earlier to ring down modeling is, for instance, mode mixing. So we said that it's kind of natural to expand our solution into spin-weighted spheroidal harmonics. But when we want to write then an expression for our modes, we want to really work with spin-weighted spherical harmonics. And then when you write down your final strain, then you get in these mixing coefficients that I mentioned earlier when you try to expand from one base to the other. So that means that you have some mixing between neighboring modes. For instance, this is an example of what you get when you look at the phase derivative in frequency domain, something that we model in frequency domain models. And normally you expect something like this, with this kind of Lorentzian shape where the frequency of the ring down is. Well, when you have mode mixing, you have some interference. So this would be in red the frequency derivative for the 3-2 mode that mixes with the 2-2 mode. And you get this kind of bump here. You don't get the nice Lorentzian shape that you get for the 2-2. And you get this bump exactly where the frequency of the 2-2 mode is. So this is telling you that there's some kind of mixing between these two components, these two modes. Okay, so now just very brief. You might think, okay, but people talked a lot about second order. What about doing second order also for ring down? Because in principle, you can just go up one order and study the effect of the next order on the signal. And as Anna mentioned, then you pick up a source term that essentially is coming from a mixing term that include your first order perturbation. And it's customary to say, okay, if I already solved the first order equation, then I know the value of these first order perturbation, and I treat them like source terms. So even if I start with a vacuum equation, then at second order I end up with a source equation. And this is also going to give me some extra feature in the ring down signal, because if you think about the previous ansatz here, if I even just naively say take products of two quantities like this, you can kind of imagine that then you get new modes that are called quadratic quasi-normal modes. whose frequency is just the sum of two quasi-normal modes at linear order, for instance. And this has already been done for Lisa, so by one of our participants. So I just wanted to say you can check this out to check detectability prospects for Lisa of these effects. And then I will leave it to Eleanor if there are no questions. Oh, sorry. Question.
Small question. So on mode mixing, you mentioned this conversion between spheroidal and spherical harmonics.
Mm-hmm.
Why would you prefer one over the other? What is the physical meaning?
Yeah, because as we said, when you separate the Tucholsky equation into a radial and angular part, the eigenfunctions of your problem for the angular sector are the spheroidal harmonics. So it's kind of natural to think that these are the ideal basis function for you to express your ring down signal. In fact, when you try to plot for instance, the frequency derivative, like I did in the slide in the spheroidal basis, you still get the nice Lorentzian behavior that you would get without mode mixing, because on that basis you don't get any mixing. They are separated, the 2-2 and 3-2. But when you go back to the
Yeah, I guess my question is why go back?
Oh, because this is standard. I mean, in waveform modeling, you express the strain in terms of spin-weighted spherical harmonic modes. This is completely standard because for the rest of the signal,
like for the observer, that's what matters. Like
yeah, exactly. This is a natural way to express your complex strain with respect to this basis. And the spheroidal harmonics basis really crops up as a more natural basis only in the ring down. So that's why then people say, okay, it's really much better to convert back to the basis that works for everything else than this.
Okay, thank you.
Okay, if there's no other questions.
Oh, sorry.
Mic switching.
Okay. Do you need to move the... So yeah, I'm now going to be talking about numerical relativity, which is used primarily for the merger and ring down part of the signal. The focus of the...
Yeah, but for the...
There's going to be both.
Oh, okay.
I don't know what's best.
You can stay there and just turn it on and off.
Pick your poison.
Okay. Okay, yes, so the first part of what I'm going to be talking about is going to give the very sort of brief flyby overview of going from the concept of what is numerical relativity to the setup of how we construct numerical relativity. I'll try and give a lot of the key equations, but there will not be time to do any of the major derivations. So if anyone wants to know any more detail about this later, then I can point you to lecture notes or textbooks that go through this in more detail. Hopefully we're just going to go through a bunch of the most key physical concepts now. I will be, yes, both talking and having slides and writing, so let me know if I'm either too quiet or writing too small. So essentially, numerical relativity attempts to solve the Einstein field equations on a computer. I will be focusing largely for the first part of the lecture on the Einstein field equations in a vacuum, because the introducing matter effect could be its own entirely separate lecture. So we'll stick with the vacuum field equations for now. Oh, stupid. Essentially, the Einstein field equations relate the 10 metric components of G alpha beta to the 10 components of the energy momentum tensor. And as Marta described on the first day, these must first satisfy the Bianchi identities. Which give 4 constraints, and then they must further satisfy coordinate transformations, which give a further 4 constraints. And we end up with 2 degrees of freedom, which will be important to remember for later on. So with numerical relativity, we are attempting to solve a Cauchy problem, which is when we construct the solution to a set of partial differential equations given data on some sort of initial hypersurface. This essentially corresponds to us then having this initial hypersurface, which we then evolve forwards in time steps. So we can think of this initial surface that we're going to do as, for example, 2 black holes a given distance apart, each with a given momenta, and then we want to evolve them forwards in time. How does that work? Okay, so this is the most mathsy rigorous bit. Hopefully, the concepts make sense, even if you're not super familiar with differential geometry. I'm not sure how many people are very well versed in differential geometry. Okay, so we have our manifold M, which is a Lorentzian manifold, has a metric, a general metric, G alpha B, which has signature +2, so it must admit one and one only time-like direction. A Cauchy surface is a space-like hypersurface embedded within the Lorentzian manifold M, such that each time-like or null curve within this surface without endpoints intersects it exactly once. The space-time, the entire space-time, is globally hyperbolic if it admits a Cauchy surface. Now, if we have a surface that is globally if we have a space-time that is globally hyperbolic, then the set of all Cauchy surfaces within the space-time is called a foliation of the space-time. Essentially, physically, okay, we are separating out our space-time into a set of hypersurfaces, and this set of hypersurfaces is the foliation. And we're going to label our hypersurfaces here by some parameter t. We conveniently choose t because this will turn out to be our time coordinate later on. But essentially, for now, t is just some constant. On each of these hypersurfaces, t has the same value. So here it's t1, here it's t2, here it's t3. All right. Now, in order to go from one hypersurface to the next hypersurface, we must first be able to define our normal to the hypersurface. Since the hypersurface is of constant t, then the normal to the hypersurface is given by taking the covariant derivative of this constant t. To get the unit normal, we just define our unit normal n, which is proportional to the normal, and we can compute the value of alpha, since alpha is just given by and this quantity alpha is known as the lapse function. And what the lapse function does is it relates the coordinate time, labeled by our parameter t on the hypersurface, to the proper time that an observer observes for the system. And when we want to go from one hypersurface to the next, then this normal evolution vector carries points from one hypersurface to the next hypersurface. To complete our description of foliating this spacetime, we want a time derivative, which must be a dual to our hypersurface sigma t. And so we define, sorry, that's gone a bit funny there. That should read, so essentially we're going to say that our time derivative, dt, is given by the normal plus some component which lies within the hypersurface. And this component, beta mu, is known as the shift. And so in order to compute, essentially, we can show that this quantity is the proper time derivative, because we know that in order to be the proper time derivative, it must be dual to our hypersurface. And so if we work this out, then we get where these two are orthogonal, so that goes to 0, and we just end up with +1. So that's all fine. No. And in addition to this, we now have our proper time derivative, and we also need to know what is the induced metric on our hypersurface. So we have the sort of global metric for our entire manifold, but we want to know what is the three-dimensional metric on our hypersurface. And we do this by projecting the metric of 4 dimensions into 3 dimensions, which is defined, any projection of a metric can just be given by this formula. And if you work this, so these two x's are vector fields within our manifold. And if we work this through, then we end up with this expression for the induced metric. So now we know what everything looks like on our hypersurface. That's given by the induced metric on the hypersurface. And we also know how to evolve from the metric on one slice to the metric on the next slice. These are given by the lapse function alpha and the shift beta, which tell us how the coordinates evolve along the proper time direction. Alpha tells us how much proper time elapses between the time slices when we are moving along our normal vector, and beta tells us how much the spatial coordinates are shifted with respect to the normal vector. So as you move along your world line, you don't move normal to the surface. How much of those coordinates shifted as you go from one slice to the next slice? Okay. All good so far. Excellent. Now, having got how things look like on a single slice and how that slice evolves from one to the next, we want to know what does this hypersurface look like within the global manifold? How is it embedded within the manifold? And this property is captured by a quantity called the extrinsic curvature. Essentially, if we are at a point P on our hypersurface and we want to move to a point Q, then if we have some vector n, which is normal to the surface at P, when we parallel transport it to Q, it will no longer remain normal to the surface. And we want to know by how much does this vector change relative to the normal as we parallel transport it along this curve. So if everyone remembers the equation for parallel transport along some vector v, then we have this. And we also have that the inner product of a given, of a vector with an arbitrary vector field is given by this. So if we take our vector y is some vector lying within our hypersurface, then at point P, then the dot product between y and n will be 0, because n is normal and y is inside the surface. But then as we parallel transport this quantity along the curve, we find that this is no longer necessarily the case. So this part contains our original parallel transport equation. So this goes to 0, but we have an additional part left over, which is not 0. And so we know that this vector n alpha is no longer normal to the surface once we have reached point Q. And essentially, this deviation from the normal is a measure of how the curve embedding of sigma is within our manifold M. This is the extrinsic curvature. So we want an expression for the extrinsic curvature, and we can think of the extrinsic curvature physically in terms of the acceleration of a normal observer. So the acceleration of a normal observer is essentially 2 time derivatives. This relates it to the normal in this way. And from that expression, we can derive the extrinsic curvature. We can also think of the extrinsic curvature as the Lie derivative of the 3 metric. So it gives a sense of how the 3 metric changes as you sort of project it along the normal. For those not familiar with Lie derivatives, I'm not going to go into them here. So that's just a side note. Okay. Is that all clear so far? We now have all our components that we need in order to start putting together what are called the ADM equations. Sorry, the ADM formalism. Essentially, we have everything that tells us we start with one spatial metric on our hypersurface, and that spatial metric is embedded as described by the extrinsic curvature. And now we want to evolve this whole system forwards in time in order to compute, how our black holes evolve. To do this, we have to recast our Einstein field equations in terms of a 3+1 formulation that Anna referred to on the first day, I think. And this recasting the equations into a spatial component on our hypersurface and removing sort of the time derivatives that allow us to evolve it forwards allows us to take these sort of snapshots. Yes. Am I out?
Is that okay if I ask? I would have thought, but maybe it's a little bit silly, but that's the extrinsic curvature would contain all of the information about the metric itself. But it seems that no.
The extrinsic curvature, you mean?
So when you do your foliation of your space, it is somewhat linked to the metric of your space.
Yes, you mean the global
the global
metric.
one, yes.
Yeah.
And because the your spatial metric is just the projection on one of your hypersurface of that global one. I would have thought that the extrinsic curvature of that foliation is entirely defined by that spatial metric.
By the global.
By the global that you projected.
Okay. So essentially, we can see from this, I'm not entirely sure I completely follow your question. Are you saying you think that from the extrinsic curvature, it contains all the information of the global metric, therefore you ought to be able to recover the global metric from the extrinsic curvature?
At least the projection of that global metric on your hypersurface.
So why do you need both?
Exactly.
Entities? I mean, in the sense that it's given by the Lie derivative of the induced metric. So the induced metric will be the information on the foliation, and the Lie derivative along n will contain the information about the moving from one slice to the next. So yes, I think it should have basically all the physics in there, and it depends on the locally defined metric.
Okay.
So I guess you don't need both, but you need one to get the other.
Okay. So gamma here is your projected
Gamma,
metric on your...
this is my induced metric. Sorry, I should say, I was using G for the global metric, gamma for the induced metric. Okay, so how do we get the expressions? Essentially, we want to, first, we project the Einstein field equations twice onto time. Then we project them into space and time. Then we take the Lie derivative along the normal vector. And then we project them onto space. And this is how we're going to separate them out into four expressions, which are, four expressions, still 10 equations, which are separated into sort of time and space. So, okay. This is the point where we sort of magically reintroduce the energy momentum tensor, having forgotten about it up to now. This is fine. This is all good. But we're going to, therefore, write our expressions in terms of some quantities. The energy density, which is given by this. The momentum density. And the stress tensor. Okay, so how do we project the equations twice into time? Essentially, we just multiply the Einstein field equation through by the normal vector twice. So that's one. We multiply this through, we work through all the maths, which I'm afraid I'm not going to do. It is many pages and not very interesting. Okay, then we want to project it once onto space and once onto time. So in projecting onto space, we do this with the induced metric. And projecting into time, again, we use our normal vector. Okay, when we take the Lie derivative, we just take the Lie derivative along the normal vector. And then finally, we project twice into space. And in doing this, there's a whole set of equations called the Gauss-Kordazzi-Ricci equations, which help you reformulate all of the equations when you work this through. That's partly why I'm not going to go through it here, because it's an entire additional set of.
Yes. A silly question, maybe. I'm trying to understand the different projections, and that I see that. But the third one is taking the Lie derivative. What's the physics then of that part? Because all the other steps are like projecting it on the different components.
So I think that one essentially. So the Lie derivative along mu gives you the extrinsic curvature. So that one is going to tell you how the induced metric evolves within the manifold. Taking the Lie derivative along mu is kind of equivalent to sort of, I think, projecting the spatial metric out into time, but it's not the whole Einstein equation. It's having taken. We're already cheating here because the spatial metric is already the projection of the whole manifold. So we're just looking at how the spatial metric
and
is
so it's
evolve.
Related closely to the extrinsic curvature that you find.
It's how it's evolving in time, how the curvature is evolving in time. Okay, so once we do all that, these are the expressions we end up with. The first two are the two constraint expressions. To clarify here, all symbols are now in 3 dimensions only. So this is the 3-dimensional Ricci scalar. This is the 3-dimensional covariant derivative. 3-dimensional curvature. We've moved into our 3+1 slicing. We've ended up with 2 constraint equations, which lie on our surface, and 2 evolution equations, which tell us how our 2 quantities, the induced metric, so the metric on our surface, and the extrinsic curvature, so how that surface is embedded in a manifold, how do these evolve in time? And these can be thought of as analogous to the field equations in electromagnetism. We have our 2 constraint equations in electromagnetism, which are static, right? And then we have our 2 evolution equations, which contain time derivatives. And these tell us how our fields evolve. Okay, so again here we have our 2 constraint equations, which tell us sort of static information on the surface, and our 2 evolution equations that tell us how everything evolves, nominally how the induced metric and how the extrinsic curvature evolve. Okay, so here ends the maths. Right. Unfortunately, I have described the derivation of the ADM equations because it's the original first set of equations. It's the sort of first way people did things. They are 4 equations, no time derivatives. The constraints are preserved under the evolution equations. We end up with 2 degrees of freedom, as we expected from our initial look at the Einstein equations where we impose all of our constraints. But they're not well posed, which means that when you try to evolve them in your simulations, you get singularities, everything breaks down, nothing works. So in reality, current NR codes employ alternative formulations of the Einstein field equations, and there are many, many different formulations which have been found to be well posed. The generalized harmonic gauge was the gauge and the formulation that was used for the first ever breakthrough of the binary black hole simulations in 2005. It's still used today by one of the more well-known codes, the spec code or the spectre code, which is behind the SXS collaboration, and then other gauges such as the BSSN or the Z4 gauge. These are used by current-day moving puncture codes. These two are the most widely used gauges by most NR codes. So, okay. These different NR codes, they all use different formulations of the Einstein field equations. They treat the singularities differently. They use different numerical methods. Some of the most widely used binary black hole codes are the speckle spectre code, BAM, Einstein toolkit, Maya, and Lazev. These last set are all moving puncture codes. The first two are spectral codes. And it's really great. Occasionally, we are able to collaborate as a community and actually compare the results of these codes, and this is what gives us a lot of confidence in the fact that these different formulations are all equivalent, stable, we have a handle on our errors, all this sort of thing. So, okay. These two different sets of codes, most commonly used numerical methods. We have finite differencing. Finite differencing codes, they take your hypersurface that we were thinking about, they grid it up, they divide it into these boxes. Where we have the black holes themselves, you have a much finer gridding. Further out, you have a much less finely gridded space-time. And then you compute your quantities on the hypersurface at each of the points of your grid. And then you use normal finite differencing methods to compute gradients and everything and get the quantities across the surface. Spectral decomposition is somewhat more elaborate and involved. You essentially formulate your unknown equations as a series representation of your of some set of basis functions, known basis functions phi, and then you are able to obtain the quantities that you want, your f of x, in terms of the partial derivatives of known functions phi. And these partial derivatives is then what you solve for and evolve forwards. The big advantage of the spectral decomposition method is that because you're dealing with partial derivatives, which you manipulate, your error will fall off exponentially. Whereas for finite differencing methods, where you're just using normal finite differencing approaches, your error will fall off as the error in your term to the power of n, and where n is the power of your finite differencing parameter. The two sets of codes typically also treat the singularities differently. As we were discussing earlier, you can't evolve the singularities within your simulation, so you need to somehow remove them. One option is the moving puncture approach, which is the slightly more sort of evolved one. You use your gauge conditions to kind of just remove your punctures. I think you take the lapse has to go to 0 at the puncture. Yes, so you do this by doing a conformal transformation of the spatial metric around the puncture, and this conformal transformation removes that puncture, and then you are able to decompose your spatial metric into a singular and a regular part. You evolve only the regular part. Singular part is hidden, unseen. We don't worry about it in our simulation. Excision is a somewhat more simple approach. It is what it says. You cut out that part of the space-time. Don't bother evolving it. And then finally, having evolved our black holes right at the center of our simulation, we want to be able to extract our gravitational waves, which have propagated outwards within our space-time. And we extract these at some distance away from the center. In the simulation, we actually measure the metric perturbation, psi 4, that Marta was talking about previously, which is given by the Weil scalars, and can be related back to the strain via something called fixed frequency integration, because essentially this metric perturbation, psi 4, is a double time derivative of the strain. But if you integrate this up in the normal way, via just normal integration, you will end up with a linear term plus a constant term, right? Because it's a twice integration. And you then have to be able to remove this from your waveform. So instead we do something slightly sneaky, where we perform a Fourier transform. In the frequency domain, your integral is now just given by dividing by the frequency. So we perform the Fourier transform, divide by the frequency twice, and perform the inverse Fourier transform. And in order to get rid of annoying high-frequency noise that could be picked up in your simulation, we put a cap on the frequency, and below a certain frequency, we don't. We just divide by some sort of minimum threshold. So below omega naught, we just divide by omega naught, basically. There are also, these days, more advanced methods. So some codes will just extract the gravitational waves at a finite extraction radius, and then you can perform an extrapolation if you use multiple finite extraction radii to get the expressions at infinity where they're actually valid. You can also use something called Cauchy characteristic extraction, which sort of gives you the gravitational waves at infinity sort of already. But it does still involve a bit of stitching together. So you will still evolve your space-time, and then at a certain point, you will feed the information from your evolved space-time into your Cauchy characteristic solver, and that's how you get the waves at infinity. Ongoing attempts to actually compactify the space-time, so we get the whole thing in a single simulation, are showing promise, but we're not there yet. Okay, so now that we have the whole simulation all together, we are able to extract our gravitational waveform and do all the science that we want to do with it. We can build our gravitational wave models. We can use it for injections for data analysis problems, anything that you might want to think of. But there are still limitations of numerical waveforms. It is the closest that we can get to an exact solution of the Einstein field equations, but it is only as good as the error in our simulations. So you can see here, this is the absolute error in the phase of some gravitational waveforms extracted at finite radius. So 50, 60, 70, 80, and 90 solar masses, unitless situation here, away from where we've perturbed black hole. And you can see that the closer you are in, basically the greater your error. And as you go further out and you approach infinity, the error will shrink relative to the extrapolated waveform. There's two main sources of numerical error in any simulation. The first is finite extraction radii, and the second is finite resolution. And you should never really use a numerical waveform without having a sense of what is the error in this waveform. Depending on your purposes, it might be that your error is so small in the waveform you don't care what it is, but you should still be aware that it really is there. And one crucial thing to look out for is that the code and the waveform that has been run is convergent, so they actually know what their errors are. Yes?
What's the difference between extraction and resolution?
So essentially, the extraction is how far away you are when you extract your gravitational waves, so how far they have propagated within your simulation. And the resolution is how finely have you sliced your grid, and also for the time stepping. When you evolve it forward, how big a time step are you taking? Okay. Oh, sorry. No.
So the finite resolution is related to the lapse function?
The finite resolution, yes, is the lapse, but also the shift. Yes, so the lapse, yes. The lapse is very much around the equations. Mm-hmm. The finite resolution comes from when you translate those equations into numerical methods. So the time stepping is related to the lapse, and the box slicing will also be related to the shift. But really, what I'm saying is when I when I say that I have the function of some value right, as something numerical, how big is my h is essentially the numerical value. And if I'm splitting up the lapse of evolution in time, then the error is in the time stepping, and if it's in the spatial metric, then it will be. Okay.
You mentioned that you have a bunch of extraction radii and you extrapolate to infinity.
Mm-hmm.
Isn't that a source of error in of itself?
The extrapolation can be a source of error, yes. So some codes do extrapolate to infinity and some do not. As I was saying before, with the spectral methods, a massive advantage is that the error falls off exponentially. This is great for resolution, not so great for extrapolation, because you need to be much further away to have a much smaller error. Whereas for the moving puncture codes, you actually, for this extraction radius of 90, your error is actually already getting pretty small. So in that case, you might not bother with the extrapolation. But yes, errors are introduced that way. So okay, I was going to talk a little bit about the extrapolation. You can use something called Richardson extrapolation, where your true value is given by your approximate value plus your error times your numerical parameter, and you sum over increasing orders of error. Yes?
Oh, thank you. Just, I don't know if this was mentioned, the initial conditions,
Mm-hmm.
how do you set them to, like...
How
like, is this a problem? Setting the initial conditions to something that,
yes.
you know...
Solving the initial conditions is its own separate
Okay.
setup, which, I haven't really discussed here.
Okay.
There are two stages to setting the initial conditions. One is to formulating your initial data, choosing the correct gauge and everything, setting that up. And then once you've got that set up, you can just input the masses and the spins and the separation and the momenta, and off it goes. And those parameters we take from PN often. So we evolve a PN set of equations, and then we take, the PN will say, okay, at this separation you ought to have this momenta. And we set up our black holes to have that momentum and separation, for example.
Yeah. Okay, I guess what I mean is, in practice, you just set an initial condition. If I understood correctly, you have to give the metric
Mm-hmm.
and the extrinsic curvature for like the first Cauchy surface.
Yes.
And that has to represent like two black holes, like
Yes.
something like that. So how do you get that in the first place?
You get, okay.
Like just you don't have an analytical formula, so...
You need to solve your constraint equations, basically. So these two will tell you how things should lie on the surface.
Okay.
Okay. I'm very nearly out of time. Can I answer this later? Sorry.
Okay.
It is its entire own separate problem, solving the constraint equations to get the initial data. Okay, so then you do your Richard extrapolation, you measure the convergence, check that your code is convergent, that the resolution you've run at is within the convergence regime. And then because with NR codes, you never ever get clean convergence because you will use a different order of evolution for your time stepping and for your spatial evolution. Essentially, you want to find the order which minimizes the difference between your three waveforms. And you should essentially find that the error falls off as 1 over the extraction radius. So the further away you are from the source, it goes as 1 over r. And the dependence on your resolution will depend on the order of your numerical equations. So in the code that was looked at here, you use 4th order time stepping and 6th order spatial derivatives. And so you get a sort of average of, okay, the code is about 5th order convergent. And then once you've worked out your convergence order, you can make an estimate of the error in your waveform. And then this is just an overview of all the NR catalogs that are available for use. The biggest of which is the SXS catalog for binary black hole systems, but there's a whole other set out there, and depending on the purpose, the RIT catalog, for example, contains very high mass ratio simulations. The BAM catalog focuses on a uniform coverage of the processing parameter space. And then there's a whole separate set of catalogs that talk about binary neutron star systems. So that's just an advertisement here. And I think it's that time. Okay. Great. Yeah.
It's just a short thing. I just wanted to get a little bit more information on sort of the effective difference between those different singularity treatments, the moving puncture and the excision. Like, it seems like in both, you're basically just sort of getting as close as you can really manage and then just ignoring what's inside. Is that an oversimplification?
No, that's pretty good.
Okay.
Yeah. No, I think that's... Okay. I think, in theory, the moving puncture one is slightly neater because you don't actually throw anything away. You use this conformal transformation of the metric. That means that you can keep evolving the whole thing, but you've removed the sort of singular term.
Yeah, you're sort of just finding a part that you assume basically doesn't change the whole time,
yeah,
as opposed to just not doing anything.
Yeah, whereas excision is like, we have to track our points, and then we have to make sure that we, you know. But so in the excision case, that will move. You have to track where the singularity is at all times, and so you drop the points where the singularity is. Mm-hmm. With the moving punctures method, the punctures kind of stay fixed, and you're able to, because you don't evolve the singular part. So you just evolve the regular part, and so you can forget about the singularity entirely.
That's interesting, how the moving punctures is the one that basically doesn't move. And that's not a question.
I was wondering, so if you're using only like a finite volume for your for the numerical treatment, what do you do at the boundary?
So there are two different sort of approaches to this. Most moving puncture finite difference codes will essentially set their boundary to be causally disconnected from the center of their simulation. So nothing that enters from the boundary should ever affect the simulation. It's far enough out. So if you want a waveform that is 2,000 m long and is extracted 100 m away, your boundary must be 2,100 m away. And ideally a bit further, right, because you don't want things to interfere. You obviously do have boundary conditions still, but you say you're safe when it's completely disconnected. For spectral codes, it's much more expensive, so they will be much closer in. So they have to be much more careful about their boundary conditions. But you'll still have reflections at the boundary from the numerical code, and you'll still have, at the very start of the waveform, you get a spike of junk radiation, which is because the initial data that you provide is never exact. And so as your simulation sort of settles down, this pulse travels outwards. It will hit your boundary. If your boundary is not causally disconnected, it will come back. And so you have to have a lot of dissipative terms in your evolution to basically get rid of the noise so that you can still extract your signal.
Thanks. Eleanor, which codes use which treatments?
SPAM Einstein toolkit, the finite difference codes will use the moving puncture method. The spec code uses the excision method. But there is some crossover. You do get some finite difference codes that also use the moving punctures method.
Oh, yeah, okay, sorry. Yeah, I also have a question about initial conditions, like how to estimate it's good or not, or how to optimal it.
Do you mean the formulation of the initial conditions, or do you mean the initial data that we input taken from, say, the PN equations?
Maybe you can explain both, or just briefly. Yeah.
So in terms of the input data, you can input anything and see what happens.
Yeah.
And in some cases, you'll just end up with a head-on collision, or if it's really wholly wrong. I once had a colleague who set them up and they ran away from each other. So generally, we use PN, or you could use other waveform models to say, for a binary that has this mass and this spin at this separation, this is the momentum that you want. It's never right. For our NR simulations, particularly again for the moving puncture finite different codes, spec starts a lot earlier in time, so they don't have this problem as much. But our PN is already breaking down often at the point at which we start the NR. And so there will be some error, partly why you get the junk radiation, but also we say we want a quasi-circular system, and we set it up and we find it's eccentric. And basically all we can do about this is perturb the initial conditions and try again until we get something that is close enough to quasi-circular. And there are lots of fancy methods to say, maybe you just do a numerical change and you grid up the space and you run hundreds of simulations. Maybe you use eccentric models to try and say, okay, my eccentricity is here, so I think I should move this far in the momentum and choose this perturbation. But it's just trial and error. There's no analytic way of doing it. With the Bowen-York initial data or one of these formalisms, that is something that has been worked out numerically and has been tested to find that it's well posed and everyone's happy with it. And then, once you've found an initial data setup that works, just use the one that works.
Thank you.
I think you mentioned the implementation of space-time compactification is under works. Would that reduce the finite extraction radii, sort of error? Would that reduce that source of error a bit, or not?
Yes, I don't know exactly how that error would come into play, but essentially, yeah, we would be extracting at spatial infinity.
Right.
You would still have propagated a distance out, so you'd have to have a sense of how far numerically your waveform had traveled in order to get that. But theoretically, yeah, that should go away. We shouldn't have that source of uncertainty if we do the compactification.
Okay, thanks.
Okay, so since you have probably looked at lots of these simulations, what happens when two black holes merge? I just imagine the two event horizons, at some point they touch, and now you have one big event horizon. What happens to the singularities inside?
Well, we don't evolve inside.
You don't evolve inside.
We don't know what happens to the event the singularities themselves once we're inside the horizon.
But if you don't evolve the part inside, why do you need to treat singularities?
Well, we still can't see the singular part of our equations. So there's still a part that has been transformed away that we don't see. I mean, you can track the horizon. What we do, we track the horizon of our black holes, and you can see that at some point the horizon goes from being here and this size to being here and that size. But we don't know what happens to the puncture.
Okay.
All right. On that note, I think it's time to thank our speaker again. And all the speakers from today. Thanks, Eleanor. And yeah, I think that was a good full day of lectures. Let's meet in 50 minutes at the restaurant.